I'm Keenan.
I'm Danielle.
And I'm Miho.
And today we're going to talk about chiral drugs, enantiomers, and thalidomide. In 1956, a West German pharmaceutical company created thalidomide. It was meant to be an anticonvulsant drug, which is used by patients who experience epileptic seizures. It had sedative properties. It made people tired, drowsy, and many people began using it in this manner. Originally, it was tested on lab rats, and the manufacturer found that there was no lethal dosage level, and so it became incredibly popular on the fact that it was safe and that people couldn't overdose on it. It was a non-prescription over-the-counter drug, meaning it was very easily accessible, and so it became very popular among European countries. However, suspicions arose. As time went on, many users started experiencing nerve damage. In the United States, the FDA never approved of it, despite constant published research by European scientists. And most severely, many babies were being born with phocomelia, a condition in which the limbs form very close to the trunk of the body and are very badly underdeveloped. It caused around 10,000 birth deformities around the world, and only around 50% of these babies survived. As you can see in the picture in the top right, the child has a prosthetic arm, and many of these children were handicapped for their entire lives. In 1961, Dr. William McBride, an Australian obstetrician, suggested the link between phocomelia and thalidomide, and it was taken off the market the following year. But why did this happen? Thalidomide exists in two forms, which are called enantiomers, one which acts as a sedative, and the other that is teratogenic, disturbing the development of the embryo. During testing, there was never any experiments done on pregnant rats, which would have drawn out the problem. So when pregnant mothers started taking thalidomide as a morning sickness pill, the teratogenic form began attacking their fetuses, causing irreversible damage. Drug isomerism, as seen with thalidomide, is important in the field of pharmacology, as isomers differ in their pharmacokinetic and pharmacodynamic properties. Drug isomerism helps us create safer and more effective drugs. Enantiomers are a crucial part of the pharmaceutical industry, since one chiral structure can lead to the desired effects, while the other can be detrimental, as seen in thalidomide.
So what is an isomer? Isomers are molecules that have identical atomic composition, so they have the same molecular formula, but they differ in the arrangement of those atoms. They can differ spatially, geometrically, or in bond formation, which leads to them having different properties. Two types of isomers are structural isomers and stereoisomers. They can be further divided into groups of constitutional, configurational, or conformational isomers. Structural isomers are also known as constitutional isomers. They have the same molecular makeup and atomic composition, but different bonding arrangements between atoms. For example, pentane and isopentane have the same molecular formula, C5H12. However, the arrangement of the C and H atoms are different. Pentane is a straight chain 5-carbon compound, while isopentane is a branched isomer. And because they have different structural compositions, they have different properties like different boiling points. Stereoisomers are molecules identical in atomic constitution and bonding, but are arranged differently in 3D space with different spatial orientation of bonds. There are two different types, conformational and configurational. With conformational isomers, the bonds are not broken, but rather are rotated around the sigma bonds. As seen with D-alanine and L-alanine, the bonds are simply pointed towards different directions. In L-alanine, the CCH3 and COOH vertical bonds point away from the viewer, while in D-alanine, the CH and CNH3 horizontal bonds point towards the viewer. With configurational isomers, bonds are needed to be broken to convert the isomers. For instance, this can be seen with trans-2-butene and cis-2-butene. The two stereoisomers of 2-butene differ in the geometric arrangement of the groups attached to the double bond. In cis-2-butene, both methyl groups are on the same side of the double bond, while in trans-2-butene, the methyl groups are on opposite sides of the double bond. The two isomers have the same structural framework, but they differ in the arrangement of this framework in space, so they therefore are classified as stereoisomers. However, they are specifically configurational isomers, since the isomers do not interconvert without breaking the double bond. The double bond present is rigid and the parts of the molecule are not free to rotate with respect to each other about this bond. So if two isomers are superimposable, that means they are identical and they are the same molecule. But if they are non-superimposable, then they are called enantiomers.
An enantiomer is one of two stereoisomers that are mirror images of each other, but are non-superimposable, or they are not identical. For example, look at your right and your left hands. They are the same except for the opposite orientation. They're mirror images of each other. If you took your left hand and placed it on top of your right hand, face up, they do not fit. This means they are non-superimposable. Technically, they are isomers. The same goes for molecules. Looking at the molecule on the left, you can see a tetrahedral structure with a carbon on the center, with a hydrogen, fluorine, bromine, and chlorine atom attached to it. On one enantiomer, the bond of the hydrogen molecule is indicated by a darkened bond, meaning it's closer towards the viewer. The fluorine atom is indicated by a dotted bond, which means it's further away in three-dimensional space. And the enantiomer on the right, the fluorine atom is closer, and the hydrogen atom is further away. The two molecules have the same atomic makeup but are structured differently, and therefore have different chemical effects. Most optical active drugs are chiral as a result of the presence of asymmetrically tetrahedral carbon atoms, like the one on the previously shown molecule and the one in this image, as you can see here. The individual mirror image forms of a chiral molecule are called optical isomers because they rotate the plane of polarized light. In other words, they are optically active and differ in structure only in the orientation of atoms. Today, optical isomers are more commonly referred to as enantiomers, or an enantiomeric pair. Thus, optical isomerism is referred to as enantiomerism. Optical isomers, or enantiomers, have the same physical and chemical properties like identical melting points, solubility, and so on. But the important difference between the two is that each member rotates the plane of polarized light to the same degree in opposite directions. Isomerization or enantiomerization is the conversion of one stereoisomeric form into another, such as R-ibuprofen into S-ibuprofen. When isomerization occurs by the change of configuration at a single chiral center, the process is called epimerization, and when it leads to the formation of racemes, it is called racemization.
When produced through normal reactions, enantiomers are naturally formed as half of one chiral structure and half as the other, the R and the S, respectively. These structures follow a lock and key model, so one will be the active structure, which fits into the desired receptor in the body, depending on the desired effect of the drug. The other will be inactive, not having any effect because it doesn't fit into a receptor. Or it could have other undesired effects by fitting into a different receptor, and this is what happened with the thalidomide. However, tests must be done in order to determine whether a single enantiomer drug or a racemic mixture is harmful to the body. Take citalopram, which is an SSRI, or a specific serotonin reuptake inhibitor, an antidepressant. The S enantiomer is 30 times more potent in inhibiting serotonin reuptake. Studies have shown that the pure S enantiomer drug works better than a racemic mixture of S and R. You can see that the two carbon bonds in the center are isomeric. In the S enantiomer, the carbon within the amine group at the end is bonded away from the viewer. In the S enantiomer, the carbon with the fluorine at the end of it is bonded towards the viewer, and this accounts for the differing effectiveness of the drug. On the other hand, in fluoxetine, which is also an antidepressant, the R and the S enantiomers are both effective at blocking serotonin reuptake, but they are metabolized differently. When trying to utilize them in pure enantiomer mixtures, it was found that R inhibits cytochrome CYP2D6, which is a protein crucial in the metabolic processes of the body, thus causing harm to the body. Together, however, as a racemic mixture, fluoxetine is a safe antidepressant and is widely utilized. Citalopram and fluoxetine are two of the many examples that support the fundamental idea that in order to determine whether it is safer to use a racemic mixture or the pure enantiomer drug, it must be tested, as it differs on a case-by-case basis. Thalidomide, however, is a special example, and scientists are unsure of what happens. In the case of thalidomide, separating the two enantiomers has little effect on its effects on the body. Thalidomide has a chiral carbon, which is unstable and allows two enantiomers to coexist, which can interswitch between the two states rapidly in bodily fluids and in water. More specifically, the nitrogen and hydrogen in the center are interswitching. Thalidomide exists in two mirror image forms. It is a racemic mixture of R and S enantiomers. The R has sedative effects, whereas the S is teratogenic, which disturbs the development of an embryo or fetus. Under biological conditions, the isomers interconvert, so separating the isomers before use is ineffective. Even in testing, it is incredibly expensive and difficult to keep the enantiomers separated. Thalidomide was sold as a racemic mixture, or containing both enantiomers. It is unknown as to why the S enantiomer is teratogenic. Since the molecule interswitches in vivo, scientists have a hard time studying it, but there are many theories that try to explain it. It has a very complex structure that makes it difficult to determine why it causes limb deformities. There are some possible explanations. 1. Some studies in rats have showed that thalidomide inhibits angiogenesis, or the growth of new blood vessels, in chick limbs and rat eyes. It can also induce cell death in certain limb tissues, but it is uncertain as to why only in limb tissues. It can also block growth hormone signaling during limb formation. All of these are possible explanations as to why thalidomide caused the birth deformities seen in the 1950s.
So, to bring everything together, enantiomers are molecules that are mirror images of each other, and this small difference has the potential for substantial consequences. Different enantiomers of the same molecule affect the binding ability, as previously mentioned with the lock and key model. The failure to recognize this difference can lead to tragedy, such as that of the thalidomide disaster. Hopefully, as the pharmaceutical industry grows, research about the effects of detrimental enantiomers on the human body will also expand, allowing for safer drugs to be created.